So one of the popular challenges at the moment is to develop the so-called intelligent personal assistants. The idea is that an artificial intelligent device should be able to analyze vast amounts of specialized literature, for example, in medicine or in law, and should be able to provide valuable advice to highly skilled professionals, and of course also to even lay humans who are not maybe working as medical doctors. They might benefit from the advice of AI too. It sounds really fascinating because the amount of information available at the moment is simply unsurmountable for any single human. We simply do not have big enough memory to read all the available literature, and it is also appearing every day. However, I would like to attract your attention to some reservations I currently have about the possibility to delegate an essential part of our current duties, such as searching for literature, analyzing literature in a meaningful way, to artificial intelligence, because it is very well appreciated that if we are not using certain skills, we are losing them. For example, we lost our skills of hunting or for looking for good herbs to cure us, and our handwriting skills are deteriorating slowly because we're not using them, and we do not like to do calculations in our heads or on paper at the moment because computers can do it much better than ourselves. However, the question arises, if we delegate very important decisions or suggestions or advice to computers, can we trust the computers to provide an unbiased and correct opinion solution if humans will not be able even to verify it? So I would like to invite you to think about it. However, it is not rather the traditional style artificial intelligence which worries many people. Because, to be honest, the term intelligence in the AI might be quite misleading. Intelligence in modern AI might look spectacular, but it is really a little bit limited, because after all the modern intelligent devices are performing a sequence of operations which are prescribed by a human, by an intelligent human, who is a truly intelligent system. And the scope of the problems does look spectacular, but technically we might describe it as largely recognizing a familiar pattern and attaching a certain decision or action to it. For example, find a dangerous item in the luggage and raise an alarm. Modern AI technologies are not thinking like humans at all. They do not attach any meaning or understanding to the patterns they discover or recognize. They cannot survive without humans, and they have very limited creativity. The question arises, if the human-like intelligence can be possible, what are the associated dangers? Because if the device thinks like a human, it will develop the mind of their own, and maybe such devices might eventually regard people as competitors or as a threat, or maybe just unnecessary creatures, and maybe take steps to eliminate them. So these fears are very widely popularized now at all levels. Is the artificial general intelligence possible at all? There are two viewpoints. Some people, including very big names, highly intelligent people such as Elon Musk and Stephen Hawking, believe AGI is possible almost around the corner and warn us around this. And some people say that it is only a mere speculation, and such people involve Marvin Minsky, who is regarded as the father of modern artificial intelligence, as well as many experts as well. In my opinion, it is really difficult for us to judge which viewpoint might be plausible, because there is no formal, explicit definition of intelligence at the moment. So what would we regard as an intelligent system? And a recent paper, co-authored by one of the panel members, Shane Legg, who is present here, and also by Markus Hatta, collected over 70 definitions of intelligence available at that time, and analyzed them. And it appeared that definitions of intelligence, first of all, strongly depend on the field of research. For example, for psychologists, intelligence is not the same as for computer scientists or for neurobiologists. And I particularly like the quotation used in this paper as well by Sternberg, who said that viewed narrowly, there seem to be almost as many definitions of intelligence as there were experts asked to define it. So no good definition, no uniform definition is available. And the authors of the same paper provided their own summary of what an intelligent system might be. Intelligence measures an agent's ability to achieve goals in a wide range of environments. It sounds a perfectly plausible definition. However, I have a problem with this because this definition assumes that a cognitive agent has goals posed for it. So it does not pose the goals for itself. But humans are not like that at all. No matter what our parents or our teachers are telling us, we can still do stupid things. I would like to look at the intelligence and at the definition of intelligence from a slightly different formal language. So it is very well appreciated that humans continuously monitor the environment and learn from their experience, and they adapt their behavior with account of this experience. We can say that the humans self-organize their behavior. And it is not unreasonable to assume that human behavior obeys certain rules. These rules will be deeply hidden, inaccessible for direct measurement, but there might be some rules. The behavior, on the contrary, is very well accessible. You can register it, you can analyze this. So making the next step, it is not unreasonable to say that the humans are able to self-organize the rules of their behavior autonomously, because nobody else can imprint the rules of our behavior for ourselves. People or the environment can influence our rules, but not determine them. And my proposition here is to consider intelligence formally as just the ability to self-organize the rules of one's behavior with account of the environmental influence, as opposed to self-organizing the behavior itself. And as a mathematician, what can I say about rules, about defining the rules of behavior? Well, there are at least two opportunities. One is through a computer algorithm. This idea was largely developed by Alan Turing in 1940s, 50s. And just to emphasize here, that in such case, the rules for a computer are determined by a human, and computer can demonstrate all sorts of behavior, but the rules will still be the same. The computer is not changing these rules. The second option available in mathematics is through a so-called velocity vector field. And this is the idea introduced by Henri Poincaré at the end of the 19th century. He was a very famous mathematician. It might take you a little bit of effort to understand the concept of the velocity field, but just to give you the idea of what I have in mind, it might be important. So consider any spontaneously evolving device or organ. It could be a human cell or a mechanical clock. Look at this mechanical clock. If we want to describe the fluctuations of the pendulum of this mechanical clock, which, by the way, occurs spontaneously without human interference, what do? We need to single out all quantities which change in time. We call them x1, x2, etc. There are n of them. And we appreciate the following, that at every time moment, the rates at which these quantities change as well. So now they're different from what is going to happen in a second, and so on. And also, it is very well known, at least in mathematics after 100 years of research, that the rates of change now are determined by the state of the given system at the moment. And what does it mean, determined? It means that the rates of change, I will point in this direction, this is rate of change, the time derivative, is the function of all system variables. So if we find these functions, we determine the rules underlying the behavior of our device. And what is critically important here, that these functions V are fully determined by the physical architecture of our device. So just to continue, the velocity field can be understood as follows. So at every, we have an n-dimensional space characterizing all possible states of our system. And at every point of this state, we can define the vector called velocity vector. And its components are these velocities introduced on the previous slide. So when we set some initial condition, the velocity field, this velocity vector, will dictate where the system goes next. So the velocity field is perfectly static. These arrows are not changing. But it can produce many, many different behaviors. In fact, infinitely many behaviors. So just to reiterate, a physical device, by virtue of having a certain architecture, creates a certain velocity field in some n-dimensional phase space. And when I say creates, you might think, is this field even real? Does it exist? Well, it is as real as a straight line. And we can say that, for example, this desk, by virtue of having a certain shape, creates a straight line. If we can say so, then in the same sense, velocity field is real. Then how can we make intelligent devices? So that's the following observation. In different devices of very different origins, such as a mechanical clock or, for example, a cardiac pacemaker cell, the velocity fields can be very similar and they can have very similar behaviors. And if we are talking about a computer analogy, it is the same as saying that the same software can be run on different computers. But now I'm talking about analog devices as opposed to digital. Then it is known that if you specify a certain velocity field, it is very often possible to implement it in an electronic circuit. And also one more observation. If we look at the brain is just a device, highly complex, but a device with a certain architecture, and it also has a velocity field. But its architecture is plastic, and by modifying spontaneously its own architecture, the brain is spontaneously modifying its own velocity field. So we can introduce the concept of the spontaneously modifying self-organizing velocity field. These ideas are summarized in these two papers available from archives. So if you are interested, please feel free to have a look. Then what we do next? We conceptually separate the velocity field from the device which produces this velocity field. And again, we can do this because as mathematicians, we can conceptually separate a straight line from this desk. That's okay. And then we introduce the concept of the velocity field which self-organizes itself. And we make the following hypothesis. Good, appropriate rules of self-organization of the velocity field might lead to cognitive functions. So if we can implement such rules and such a self-organizing velocity field in hardware, then we can create artificial intelligence of a new type. And we can invent, in principle, many, many such self-organization rules. Some similar to the ones existing in the brain and some very different. We tested our hypothesis using some very, very simple self-organization rules, but I don't have time to mention these rules because, well, please have a look at the paper if you are interested. But basically, some very, very simple self-organization rules already can give rise to some very basic cognitive functions, such as memorization, categorization, and pattern recognition. And to summarize, we learn from the brain, but we do not try to replicate its physical architecture. Instead, we are trying to look at its working principles mathematically. Currently, this self-organizing field is an abstract idea. We don't know how to implement this in practice. So we might need some new physical principles, some new devices to do this. But in principle, it might be possible to create all sorts of intelligent systems using this principle. And let me finish here by asking the following question. does it make sense to do research in this direction, given how dangerous artificial intelligence might become? And my thoughts are as follows. Currently, we as humans are facing a lot of really challenging, really complex problems, such as climate change, economic crisis, fuel crisis, various pandemics, and we do not even know what might come from the outer space. And we will need to solve such problems. But the scale, the complexity of these problems is so big that to analyze such problems completely, one needs to be expert in many disciplines. And unfortunately, no single human can be an expert in all disciplines. And this means that no matter how many experts we involve to make critical decisions, every single human making a decision or voting for a certain decision will only have a limited idea of what is really going on. And it is so easy to make a mistake. So I would say that, in my opinion, our future actually might depend on our ability to create a human-like artificial intelligence with much bigger memory and much faster thinking speed. So I'm finishing now, and I'm now introducing the panel. So these are the panel members listed on this slide. Thank you very much.
So thank you, Natalia, for the introduction. If there are quick questions concerning Natalia's talk, we can take them now. Okay.
Thank you. So if I understand correctly, you define the difference between AI and general artificial intelligence is the ability to modify the rules. But surely those rules depend themselves on some higher set of rules. So what's the difference between rules and behavior then? It seems that the line where you draw between behavior and rules seems quite arbitrary.
It's not arbitrary, at least from the mathematical viewpoint. It is very distinct, because talking in terms of dynamical systems and the velocity field, the same static velocity field defines certain rules. But the same rules can create infinitely many behaviors. So it is sufficient to have just one velocity field which does not change, which is not modified, and depending on the situation, the system will react in an infinitely many ways. So we can create many, many behaviors from the same rules. But if we change the velocity field spontaneously, if the rules of behavior, the velocity field, is evolving, self-organizing spontaneously, we will be changing not just the behavior, but all possibilities, all versions of the behavior which become possible.
But isn't this just a dynamical system over a function space?
It depends on what you mean. So, you know, what does it mean, a function space? The problem is here, if I express it mathematically, we impose some rules for the rules to organize. So it is like a double-layer system.
Still, it is the same.
Yeah, but that's still a dynamical system, just you're moving in a function space.
But how do you move? That's a big question. Not randomly.
You have all the possible vector fields in this function space, and now you're moving, I presume, because of sensory
Yes, but
input.
we have to decide how we are moving in this function space. That's the point. To decide how exactly we are moving, according to what rule, that's what would constitute the rules of self-organization of the rules.
Yeah.
Okay.
Okay, thank you very much. That means we can now start with the panel discussion. It's my great pleasure to have a set of amazing people on this panel. To get this panel discussion started, I suggest that everybody introduces themselves briefly and maybe summarizes what or how they would define AI. So Natalia already said defining intelligence is difficult, but maybe with artificial intelligence is a bit easier. So we maybe want to start on this side here with Shane.
Right. So my name is Shane Leake. I co-founded DeepMind. It's now part of Google, so it's the Google DeepMind Research Group. We're about 260 people at the moment and growing. Mostly researchers. I don't know how many PhDs we have, probably 150 or plus. Our mission is to build a general artificial intelligence. That's why I founded DeepMind. And we've been working on that for about 5.5 years now. And that's been, I guess some of you will know our work. It's been going pretty well. Been on the front cover of Nature twice in the last year, and recently beat the top Go player of the last decade in a 5-series match in China, which was quite well watched. Apparently, one of the games had 100 million viewers, which is pretty cool. So, in terms of how I define artificial intelligence, this is a this is a big thing for me. It was really the core of my PhD thesis. And because I felt that the biggest problem in AI was not that we didn't know what the solution was, it was actually worse than that. We didn't even know what the problem was. And so if we were to make progress, we need to sort of gain some clarity around that. So one of the things I did, as Natalia mentioned, is I started with a survey. I collected, I don't remember, something like 80 definitions from psychologists and all sorts of researchers in computer science, artificial intelligence, and so on. And what I found was that the definitions kind of cluster. There are a few outliers, but there are sort of a few main clusters of similar perspectives on of how to define intelligence. And there was one cluster, one of the big ones, arguably the biggest, that I thought was a fruitful perspective to take for the purposes of artificial intelligence. And that group of definitions defined intelligence as a property of an agent which interacts with an external environment / task / game / situation, so on and so on. So environment in the broad sense as you would think of it in, say, reinforcement learning or something like that. That the agent has there's some notion of success or failure. There's some sort of goal. If the agent were simply indifferent to its environment, then there's sort of nothing to be done. So there's nothing. There's no reason for it to care or do anything. And then the critical part is really the last part, which sort of goes back to what Natalia quoted here, which is the intelligent agents are those that can learn and adapt to perform well over a wide range of environments. So if you think of something like, say, Deep Blue is very, very good at playing chess, but Deep Blue can never learn to play noughts and crosses. Gary Kasparov can. People are very, very broad in their capabilities. They can learn to play chess and noughts and crosses and Go and poker and Space Invaders and 3D games and juggle and drive cars and speak Japanese and do mathematics and program computers, and it just goes on and on and on and on. So it's this adaptability to this huge scope of tasks and environments that's sort of the key in this perspective on intelligence. And it's something we haven't really seen much of in computers before. Computers tend to be engineered, or artificial intelligence systems, sometimes called narrow AI systems, engineered to do a particular thing. But you can't sort of take something out of the box and sort of go, well, here's a problem, I wonder if it can solve it, and give it a wide range of problems. So that's the perspective that we've taken on at DeepMind, and I think it has lots of nice properties. It separates out the what from the how, and I think that's a good property of definitions which generalize. And it's really important here because we don't know exactly the how, so you shouldn't try to define the what in terms of the how, otherwise you'll end up with a very limited definition. It would be a bit like trying to define speed in terms of carburetors and pistons. You shouldn't talk about the how, otherwise your definition doesn't apply to an electric vehicle or something else. It's measurable, it's scalable, it has lots of nice properties, but that would be a topic for a whole lecture, so I will stop myself at this point.
My name's Rob Page. I run a publishing company, and we often try to have a collective approach to a scientific or technological set of problems. So we commission writers to work with scientists to produce solutions or scenarios that the scientists on their own may not have come up with. And we encourage feedback between the two. I guess my take on artificial intelligence is a non-science one. I think it's interesting to see in Natalia's list that face recognition on Facebook is regarded as AI. I think in the non-science community, that would absolutely be the case. It feels human-like as a skill to be able to recognize a face on Facebook and suggest a tag. But other tasks, like, for instance, complex modeling of traffic systems in a city may take up a much greater amount of processing power, but that wouldn't necessarily be regarded by the lay community as an artificial intelligence. So the point at which the light comes on in the computer, in the HAL, the singularity, the point where the computers become intelligent, in the general sort of wider consciousness is a very kind of human bias. There's a lot of human bias in the way that it's defined and recognized. And it's not necessarily to do with complexity or processing power or anything else. I think there is a question that needs to be answered really with regard to motivation and interest. We can talk about tasks, or we can talk about rules. We can talk about rules of rules, and you can go up at several levels of different orders. But there is an intuitive sense in the wider public, I think, that the moment a computer or machine develops what appears to be self-interest, whether that's an individual self-interest or collective self-interest, or the moment it's given that, if you can program that, I know it sounds like a contradiction, to give a machine self-interest it sounds like an oxymoron, but if the public recognises that, or if there's a sense that the computer or machine has self-interest, or the appearance of self-interest, then there's a kind of an intuitive sense that there is intelligence there. And I think it goes back to the old dichotomy, the Turing test, which says if a machine appears to behave and respond like a human, then they're intelligent. That's at one end of the spectrum, and then the other counter-argument to that is the Chinese room thought experiment, which says, you're feeding messages in Chinese into a room where there's a computer that has learned how to speak Chinese and responds correctly. Does that computer really speak Chinese, or is it just going through a series of functions? And the intuitive response to that is no, there's something missing. The computer in that room doesn't actually speak Chinese. There's something else going on. And I think, though, that sort of dichotomy between appearance of intelligence and the sense that something else has failed to be resolved or taken much further in the public imagination.
Right. My name is Nello Cristianini. I am a professor of artificial intelligence at the University of Bristol. And I've been thinking about this for a long time. And I have asked for my chair to be a chair in artificial intelligence 10 years ago, when people were looking for every other possible definition of their work, because I think it is an interesting and important task to build artificial intelligence. And I often get telephone calls from journalists after anything, after AlphaGo does anything, I get called. And the question is often how far do you think we are from machines overtaking humans? That's the only possible frame I hear. And the answer is, this is not a meaningful question. Human intelligence has never been the standard for a machine. Intelligence existed on this planet way before the first human ever showed up. We had intelligent animals competing, fighting, looking after their offspring, communicating with each other. We are learning so much. We had animals making decisions, making plans, succeeding, failing, before the first human showed up, before the first human spoke. Forget human. If you want to understand intelligence, please. So I am very aware of how many dead ends our field has found because of these misunderstandings. So let us be very humble. Building a system that can pursue its own goals autonomously, make its own decisions, learn, plan, reason, and eventually fail or succeed in an environment that cannot be fully controlled. That's so generic, it doesn't sound exciting, but that will cover your average plant, your average Amazon bot, your robot, and so on. The goal has to be there. The environment has to be out of control, or at least partly. You know, if it's entirely random, there is no point of being intelligent. If it's entirely deterministic, there is no point of being. It has to be an environment in between. How do you control? How do you pursue your goals there? And that's a science. The science of constructing autonomous agents is artificial intelligence. Then, of course, there is a business model to AI today. Humans are a major part of it. Of course, we want machines to interact with humans. Of course, we want Siri to give us the information. But that is not the definition.
Well, I'm still Anders Sandberg. I think you might have heard my talk a bit earlier. And now I guess I'm here as a lapsed computational neuroscientist and somebody at a research group that is interested in AI safety. So I'm rather fond of Shane's definition, especially since it can be turned into a strict mathematical definition, which is a bit more hardcore. It's also a bit harder to apply to Siri, I would assume. But the problem is measuring how smart something is by various scales might be, as you say, one metric. But we also have a way of perceiving intelligence which is kind of weird. We generally tend to say that that was intelligently done when we want to reward somebody or encourage them to do it. And we say somebody is stupid when they behave in a way we do not like. There is a lot of this signaling going on. And in general, of course, when something is called artificial intelligence, it's still new and fancy. It's a bit like calling something technology. And that typically means it's newer than we are. We can remember a time before that, but as soon as it gets reliable enough, it gets boring and gray and turns into the background, and now it's just automation. So the classical joke definition of artificial intelligence is anything that has not been made yet. So chess playing is no longer real artificial intelligence. It's a solved problem. Once face recognition gets good and reliable enough that nobody cares about it, it's no longer artificial intelligence. And I think there is some important truth to that. We normally don't talk too much to each other about intelligence except for these signaling purposes. We want to figure out what should be done, what shouldn't be done. I want to tell other people what they ought to be focusing on. So I think the big core of the artificial intelligence debate is really that we have these interesting disagreements about how to make systems smart enough to function well in the part of the world we care about, to fulfill goals we care about.
So I'm Andrew Davison. I'm a professor of robot vision here at Imperial in the computing department, and I also lead the Dyson Robotics lab. So this is a lab here that works on hopefully future home robotics devices of various increasing complexity. So the main thing I've been involved with up to now is Dyson's first robot vacuum cleaner, which has a computer vision-based localization and mapping system. So my kind of main interest in intelligence, and probably the way I would define it, is in a robotics context, which is, I think not far at all from an agent-based view, but it comes down to linking sensing and action through some sort of processing. So I think anything that does that to some extent, you might think of attaching the label intelligent to, but at the very simplest end, it could be ridiculously simple. It could just have a robot that has a light sensor, for instance, directly connected with a wire to a motor so that it will tend to drive towards bright things. And you can watch a robot like that and you might start to apply words to it, like it wants to drive towards the light, it desires things. So, but then you've got a whole scale from there up to, for instance, a robot that would, have a camera, it looks at a room, it looks untidy, and it goes and tidies it up, for instance. I mean, the difference in complexity between those two things is absolutely huge. So I think the other big aspect I would always want to use when defining intelligence is that it's got to happen within a reasonable time frame. So I think when you consider a robot, it's got some kind of processor, it's got sensing, and then it's got the algorithms that are holding all that together. It's not really intelligent unless it can actually decide what to do quick enough that that decision is still useful for acting.
I'm Natalia Janssen, as you might remember. So for me, intelligence, including artificial intelligence, is the same as I already mentioned. I believe it is the ability to self-organize the rules of your behavior, of one's behavior.
Okay. Thank you very much for the introduction and also your perspective on AI definitions. So I would like to keep this reasonably interactive. So if you have questions, just raise your hand and then we'll get this going. And please let us know to whom that question is. All right. If there's nothing yet coming up, I would then continue, maybe starting at Natalia's end this time, and ask whether science fiction has influenced your work or more scientific development, and to what degree, in what extent?
That is a very good question, and I'm a big fan of science fiction. I strongly believe that science fiction is a very important part of our culture, because what good science fiction authors are doing for us, in fact, they are modeling the future, they are modeling the options, which scientists might not have enough time or means to do at the moment. So science fiction authors are investigating thousands of new worlds for us, which do not even exist. But they are trying to predict what is going to happen if a certain technology becomes available. My work was influenced by science fiction, also about artificial intelligence, in the sense that it inspired me to think about such problems. Also, it affected my way of thinking about the responsibility of a scientist for his or her research. Because if a certain research becomes potentially dangerous, and science fiction writers have been speaking a lot about the dangers of artificial intelligence, so is it ethical to even continue thinking about this research? So yes, it did affect my thinking about artificial intelligence a lot.
Yeah, I've also always been a fan of science fiction books and films. I think it's always there as a kind of inspiration of what might be possible. You know, robots that can move around and effortlessly know where they are is just something that's usually assumed to be, you know, a straightforward thing in most science fiction. So, you know, actually trying to build things like that has proven to be incredibly difficult, I think. But yeah, it's just, you know, it provides an easy way, of course, also to explain the work that you're doing to people who aren't working in this area. You can, you know, you have a language to try and explain the things you're trying to do, because lots of people can relate it to concepts from science fiction.
Well, as I also mentioned in my talk, I read a lot of science fiction, and I particularly liked those parts of the stories where you got to see the perspective from an alien perspective. Not just from aliens, but quite often also from artificial intelligences. I always felt those were really exciting, a different way of thinking, at least if it was a good author writing the story. Of course, there is something paradoxical, because a truly alien way of thinking would not be possible to understand for readers. You need to fake things in interesting ways. And this is extra true if you try to depict a very smart mind, smarter than the author or reader. How do you make that plausible? But we have been having this argument, me and my director, for a long time, whether he should read more science fiction or I should read more history books. Because as he points out, history is even weirder than fiction. And I think it's true that science fiction is perhaps extra necessary when you need to stretch your mind to perceive something. And sometimes that's also a useful way of getting relatively simple lessons that you need to have. So when it comes to artificial intelligence, I actually think Asimov's robot stories have a very important lesson. He's making up these stories and the rules in them, of course, in order to tell a good story. But the theme of all these stories are essentially, given these rules, if you follow them logically, you get an unpredictable behavior. That is something very important to incorporate in your thinking. Just because you know the rules, maybe even you have given rules, doesn't mean that you can always predict the consequences. And this is especially true for capable systems. Then we get to the next question. So how do we set up systems so we do good things? That's a much harder problem. And maybe we can't get a help there from science fiction, but if it has helped us stretch our mind and inculcated some good mental hygiene, I think that's a good start.
I am a moderate user of science fiction. I never been a hardcore science fiction reader. I've read a lot of history. I keep on reading a lot of history and non-fiction and some science fiction. But something happened recently. As I am very strongly convinced that we should be responsible for the consequences of our work, I am aware that what we do today will impact society, which is probably not true for what we did 20 years ago in this field. And as soon as you step out of this factual world of science, you feel the need to understand, speculate. What can happen if I succeed? At that time, you are in a fictional world. So I found that as I was trying to explain my concerns to others, it became nearly unavoidable to step into the science fiction territory. And I've been writing science fiction in the last few years, just as a part of that sense of we should be responsible for the outcome of our work, which is, by the way, not different from a definition I heard of philosophy. Somebody said philosophy is the science of mental experiments. And science fiction is the same. You make one mental experiment, what if this happened? And then you try to follow logically to the extreme consequences.
Yeah, I'm also a moderate abuser of science fiction. But I also think that it's important to sometimes go outside of science fiction. There are some fantastic poets, for instance, who have this question. You mentioned that the idea of what does the world look like from the point of view of a robot. You may as well ask the same question, what does the world look like from the point of view of an animal or a wasp or a bee or an insect, etc., etc. And poets do that all the time. There's a fantastic collection of poetry by the Australian poet Les Murray called Translations from the Natural World. He's a farmer, he knows all about these things, and it tries to translate the language of animals. And that's not science fiction technically, but I think we learn exactly the same sort of things, or it's as rich as science fiction can be in that way. With our projects, with Commons projects, we try to increase or encourage more traffic between scientific research and fiction. So there was one case, Professor Susan Stepney from University of York, who's a complex systems scientist, researcher. She had several attempts to get a research proposal off the ground, which was looking at using synth bio to kind of genetically modify single-celled organisms to perhaps grow skyscrapers or grow buildings. If you can tweak the DNA of tree cells, for instance, to grow into a certain shape, why can't you do that with single-cell organisms to deposit like concrete as an exoskeleton? And you can garden. The idea was not to grow a single building from one cell, but to garden various synthetically kind of modified entities into like an organic building. She tried to get that funded as a very early research idea many times, and it got knocked back again and again and again. So she put it into the short story project. So she used a writer to develop it as an idea conceptually, because there wasn't the funding for it. So there is some interesting kind of traffic between the two, and I think it doesn't always result in what the scientist thinks will come of it. I can give lots of examples. But,
Okay, I guess we've had the science fiction lovers and the moderate users over here. So I'll go for the other end. I tend to find a lot of science fiction a bit cringy. There's a quote I sometimes give out, and maybe it's a bit extreme, but I tend to describe science fiction as bad science, often combined with bad fiction. Now, you know, there are some films and things that I really love that I guess from the science fiction genre, Space Odyssey 2001, Gattaca, recent Ex Machina I really enjoyed. But yeah, generally if I want science, I'll go to, you know, Nature or Science or a serious journal, and if I want fiction, I'll go to Hemingway or Hesse or, you know, somebody like this. But when they do get the two together and they do it well, it is very, very good. But more often than not, I am a bit disappointed.
Okay. There are questions. Let me. Okay.
Given sort of the recent successes with the supervised learning, open to the entire panel, where do you feel the focus should lie in the near future in terms of logic-based learning, or, you know, statistical methods, or unsupervised versus supervised? Where do you feel the focus should lie for the near future, and what should be the next milestone that we sort of aim for?
I can have a crack at that. I could talk about that for a long time. I mean, this is kind of all the different things we work on, all the things that I think we should be doing next. So unsupervised learning is a really big thing. We're doing lots of really great work in generative models, and it's making loads of progress now. We've got to the point where we can take 2D, 3D games and actually learn models of them purely through observation and create generative models there. It's completely unsupervised. And so you'll see some of that kind of work coming out from us. There's a few papers already, but there's much better things coming out in the coming months and so on. So I think that's a really exciting area. It's moving very fast. There's a number of good papers also in non-temporal domain of just images and so on. There's some really good work there. You can get some pretty convincing looking pictures that are just being, from a generative model, that are being imagined. They're not pictures that it's ever seen. So that's really exciting things in unsupervised learning. And then I think reinforcement learning as well is, you know, even though the field's been around quite a long time, I think it's actually relatively immature in the foundations. And there's still quite a few fairly low-hanging fruit in that area. And I think that's another good topic. And then lots and lots of different things. Integration of different sorts of things. So integrating things like you know, deep learning, these sort of massively parametric models with non-parametric models that can learn very, very quickly. And so you get interesting things like one-shot learning, generalization, and transfer happening. So I think there's some interesting things there where you start sort of bringing together the strengths of different types of machine learning paradigms and so on. I think some pretty cool stuff there.
I can add a bit. I think we are still within there has been quite a few years back the paradigm shift in AI, and we went into data-driven AI. I think we are well within it in this moment. So we are still within a statistical, data-driven normal science phase. Of course, deep learning is part of it. And so for the time being, I think we can do quite a lot within this. I'm pretty sure this is not the last thing we are going to do in AI. There will be, who knows, what other paradigm shifts in the future. But right now, we are in the middle of this phase in which data is driving things. And we haven't finished that. So I imagine quite a few years will be spent on machine learning of the subsymbolic, statistical nature, probably weakly supervised, unsupervised type of project. But I think the time has come for us socially to spend more time on integration of systems. You know, this is a different side of the question. Research does oscillate between a phase when you do systems and a phase when you want to do theorems. This is a time in which systems, I think, can pay off a lot. It's time to build stuff for a while.
Mm-hmm. Yeah, I mean, I think we're definitely seeing that in robotics now, where deep learning and other sorts of machine learning are hitting very hard now, allowing us to solve very difficult perception problems, and also directly to link perception to action. So trying to directly learn, for instance, how to drive a robot manipulator from images. But I think certainly in the next few years, combining those sorts of purely learned approaches with the more designed estimation, theoretic approaches, which we know a lot about already, will be extremely fruitful.
Okay, if I'm allowed to add a couple of words. So I would really suggest that the progress in artificial intelligence has to also be conceptual, because what modern artificial intelligence devices are uniformly lacking is any understanding, is being able to attach any meaning to the patterns they recognize. They can do the technical job, supervised, unsupervised learning, all these things, but the computers do not understand what they are doing and why. And I think some conceptual breakthrough is required in order to teach computers or artificial intelligent devices to understand the meaning of things.
Okay, there are lots of questions, so just go ahead. Anywhere.
Hi, this is a question stemming a little bit from my own research. So in the field I work in, some of the problems seem to be solved by throwing more and more computing power at it. So do you think in AI that can solve a lot of the issues, or is it mainly conceptual, as in coming up with how to do this, or is it just a matter of throwing more and more processes at it?
I think no one should underestimate just how important that is. And I sometimes wonder, I've been doing computer vision research for 20 years. If we just had the same computers as we had 20 years ago, I think we would have all given up by now. I think that's utterly crucial to everything.
I have a little story about computer vision, actually. So I think it highlights how important compute power is. So as you'll know, you can get very good results on ImageNet, sort of human comparable for classification, and you can train that up on a single desktop machine with a single state-of-the-art GPU in a few weeks. I first worked on neural nets about 1990 on a state-of-the-art desktop machine at the time, and it was a 486, and I spent a lot of time waiting for things. So as a little thought experiment, I asked myself, if I just compare how many megaflops that 486 has compared to something like a Titan Z or something graphics card today, and sort of just do the math on how long would it take, right? So if I sort of do Back to the Future style and take my algorithm today that runs on a desktop machine in 3.5 weeks, go back to 1990 and give it to myself, I'm going to be waiting a long time. So how long am I going to be waiting? After 250,000 years, you still have another 20 millennia to go. So I feel kind of sorry for people who were trying to do computer vision back in the 90s, because even the state-of-the-art algorithms today were completely unusable. Even if you ran it on a supercomputer back in 1990, a current algorithm that runs on a desktop, you're looking at 5 centuries of computation just to train the model. So it makes a big difference, and it's really important. But I think there are 2 important questions here. One is about how the amount of compute. Another one is about the amount of data. And we're getting more and more compute, and that's opening up all sorts of possibilities. But in the more and more data question, in some applications, yes, there is lots and lots of data, and you can get lots of data, and so you can go down that path. But in some applications, you can't. There are certain limitations on the amount of data you have. So there are still lots of challenges there, and we need to be thinking of ways to increase the data efficiency of a lot of our algorithms. At the moment, we're probably very wasteful because there's a kind of gold rush, and we have all this compute power. In some domains, we have massive quantities of data, so we just get lots of compute and a big deep learning model and pipe lots and lots of data through it and doing amazing things. But I think a lot of the progress will become in increasing the efficiency of that.
Yeah, just a short comment. I think it has to do with science fiction as well, a little bit. There is a sort of instinct researchers have to sense where is the best opportunity. You know where you want to put your time, which is limited, and you automatically don't pursue avenues that are not promising. And I think it has to do also with the science fiction, the bad fiction idea. if something is a bad premise, you don't know how this can be possible. It's not so exciting anymore. So for a long time, I think we have been self-censoring ourselves. If we know or sense that something can't really work in practice, we probably put our time somewhere else. I've been a few times in a room where people discussed and said, what could you do if you had unlimited computing power? You know? And that's a difficult thing. We are automatically trained to not dream in this way. But now we can think, if you don't have computing power limitations, what can you do? And if you can do this exercise, you change the quality of what you can dream. And the same for unlimited data. Or what if you had unlimited something else? What if MP was equal P? So these are exercises that allow you to do things that should be potentially not sensible to pursue, but they become sensible because now you don't block yourself from dreaming in that direction.
I think one of the really important things to think about is computational complexity here. And it's all very well thinking, yeah, in the future we're going to have lots and lots of compute power, but you have to ask yourself, what is the computational complexity of your algorithm? So people back in the 90s that were working on neural networks, yeah, they didn't have the compute power to do all sorts of really impressive things they can do now. But neural networks are fundamentally linear complexity in all the main, important dimensions. And so what that means is that as you have this exponential increase in the performance of computers, when you have a linear complexity, fundamentally parallel algorithm, you grow, your performance of your systems grows in an exponential way. If your algorithm is, exponentially expensive, then yeah, you can do more today than you could have done in the 90s, but not really that much more. So you should always be thinking about the computational complexity and things like whether an algorithm is inherently parallel and things like that. And that will allow you to really benefit from changing computing power.
Thank you. I'm curious to hear what the panel's opinion is on the term in the media about friendly AI, especially considering Nick Bostrom's book with superintelligence, probably prompting Elon Musk and Stephen Hawking raising alarm bells, even though they're probably not experts in the field. And we've got the opposite side of things, where we've got Andrew Ng saying things like worrying about overpopulation on Mars. We have Robin Hanson thinking it's centuries away, even with exponential increases in our intelligence. Is it a problem we should be worrying about? And if we're looking at provably friendly AI, what happens when humans are shown to be not friendly intelligence themselves?
Of course, I'm a bit biased since I'm working with Nick Bostrom, but basically I think there is an interesting spectrum of AI safety problems. The closest ones are don't squash people with industrial robots. That's purely engineering safety. It's still non-trivial and rather important to get right. Then you have things like autonomous cars. How do we make them safe enough and trustworthy enough so we might want to actually travel by them? And then you have questions about technological unemployment and how much autonomy do we want to give our weapon systems. And then you have the really distal things. When you get really smart, really general systems, how do we handle them? All of these ones are worth dealing with, but you need to handle them in very different ways. So the superintelligence problem, I think, is a potential existential risk, but it's not close yet. We don't know really how well to predict how far away it is, but it's pretty clear that we should start now because it seems to be a very hard problem. On the other hand, we probably don't need to spend all our resources on that. We want to make sure the autonomous cars don't squish people. So it's more about a distribution of labor. And then over time, as we learn more, I think we're also going to be able to recognize where the real trouble are. So at least from our very theoretical perspective over in Oxford, it looks like there's some really interesting, juicy problems that are both looking very hard and very promising to work on. But in the end, we don't think it's going to be as simple as just sheer friendliness. Most of the research have currently been about showing that current ideas on how to make safe and beneficial AI probably are not reliable enough. And the real problem is, of course, that you focus too much, as you say, on making the machines behave themselves. But the humans using the machines are another matter. We want to make sure that they cannot be misused too much. And that's a really interesting problem in organizing and engineering humans, which is typically in the political science faculty instead.
May I?
Sure.
I do have some concerns, honestly, but they have nothing to do with existential asymptotic risk. I have to confess, sometimes I feel a little bit annoyed when people focus too much on asymptotic possibilities, because it might distract our attention from very real short-term risks, which are not existential. So one thing is long-term asymptotic existential risk. Okay, it is non-zero. It isn't zero, and that we agree. And then there is something that can happen within 10 years, which doesn't threaten anybody's existence, but it isn't pleasant. And that deserves urgent attention. And I think it is something I want to mention briefly. We have transferred so much of our life onto this one single data infrastructure that is a new medium that allows us to have communications, news, transactions, and everything else. So this is, if Marshall McLuhan was alive, he was interested in how a medium like TV is not neutral. Well, this is a new medium. TV, radio, Royal Mail, books, shops, libraries, everything runs through one data infrastructure. And this is not passive like a wire of copper. It's looking back at us in expectation, trying to guess our intentions, to monetize, to infer, to steer. That's new. That is such a fundamentally new thing. We don't know how a single data infrastructure of this type is going to shape public opinion and democracy and everything else. Do we really want, we can't opt out. Already today, there is no turning it off. You don't ask a child, please don't go online. They will be crippled for life. There is no opting out. And now, in this scenario, we are deploying autonomous goal-seeking software within it. What is the effect of forcing everybody to interact entirely through this infrastructure? And this is before the Internet of Things comes online in a few years. And on that situation, you deploy autonomous goal-seeking software. That, I believe, does deserve some attention. It is not existential risk. It does change something about democracy, autonomy, responsibility, and markets, and everything else. So that is a concern I do have.
I would just like to jump in and completely agree with that. I think in previous paradigms, we used to pay for services. Now we get a lot of services free from social media, but in return, we service them. We provide social media and large organizations with all of our information, and it's us providing them. And I think I agreed with a lot of the sort of positive arguments that have been put forward today for transhumanism, for genetic modification. I really enjoyed Sarah's talk earlier. But the one thing which isn't being discussed enough at the moment or today for me is sort of sociological forces and economic drivers. I think I personally, and I think the public as well, to a certain extent, take a Murphy's Law to this. If there is ways, if there's ways of abusing this technology and this data for financial gain, it will happen. And I think we need to worry a lot more about that. There's a whole other question about digital and automated economies having no jobs in them. There will be a complete death of jobs, and we'll have to come up with some other economic model for employment. One model that's been suggested, a solution has come from the University of London, Sweden, is that we all have a citizen's wage, whether we work or not, and then we can work 3 days a week, and then the rest of the time we can be social entrepreneurs or whatever. But everybody has a minimum wage, which is half of what's called the citizen's wage, and it's a very strange kind of post-communist or uber-communist kind of solution to it. But it is the only solution it's the only model they've come up with this problem, that there are no jobs in a digital economy because of zero marginal gains and other things. Sorry, zero marginal costs.
So, with respect to the terminology, friendly AI, I believe that comes from Yudkowsky. I'm not really a fan of that term. I think it's not very serious sounding in my mind, but maybe that's my own perception of it. I prefer to talk about the ethics and safety of AI systems rather than friendly AI. Anyway, that said, I think that machine learning and artificial intelligence are making a lot of progress, and we will find all kinds of applications in the relatively near future that will raise all kinds of interesting questions, ethical questions and safety questions and so on. And it's my belief that there aren't fundamental limits, or not any relatively, near-term limits to artificial intelligence. That artificial intelligence can be, at some point in the future, we don't really know when, very, very powerful and much more powerful than human intelligence. So I think that there are a whole range of relatively near-term through to longer-term questions, very, very important questions, extremely important questions, that are not being studied very much at the moment. And some of these, some of these longer-term ones, if we had machines that were significantly more intelligent than humans, it's really hard to imagine the impact that that would have. And at the moment, from the near term all the way through to these long-term questions, as a society, we're probably spending less than 1,000th of 1% of the amount of money that we spend on ice cream on studying these questions that are radically going to transform humanity. And I think in hindsight, that's going to be seen as rather unwise.
Okay, so there was a question, and maybe we start with this, but we have to wrap up in a few minutes.
I think what I would like to ask kind of touches briefly on what both Ra and Nello were talking about. AI is in the future, but advanced robotics is pretty much a now, maybe a problem for some people. Automation has been predicted to, cut the workforce by, I don't know what sort of percentage. And it is something that I think the media kind of jumps on, and it's what the average person worries about. So my question to anyone who's prepared to answer it is, what sort of jobs would be the first to maybe go? And like what Ra was discussing, how is this going to impact the economy, and what sort of model is going to replace what we have now? Because once AI robotics starts replacing jobs, then the economy that we base ourselves on is going to have to change. Anybody?
I can be the first one.
Natalia, go ahead. Everybody else is too shy.
Yeah, I will wait.
It is a very important question which you are touching upon, because incidentally, in January this year, there was a World Economic Forum in Davos, and a separate panel was devoted to the discussion of implications of artificial intelligence. And their report, which was presented at this forum, said that about 5 million jobs will be lost due to artificial intelligence by 2020. And I strongly recommend everybody who is interested to watch the video of this panel discussion in Davos, very illuminating. And the jobs which were mentioned, for example, supermarkets. Supermarkets can be completely free from humans nowadays. In principle, self-checkout is already available. So I was really impressed when I traveled recently to some airports. I could hardly meet human assistants there, because everything is done automatically. There used to be many people in the airports in the uniform. Nowadays, they're almost gone. And you can perfectly check in, drop your baggage without talking to any single human. So this is an impact artificial intelligence is having already. So I would imagine all sorts of routine jobs which do not require much true intelligence might be easily gone. Receptionist, for example, check in, check out, it's easier.
So the study which is quite often quoted is by Osborne and Frey. A very famous or infamous number is 47% of all jobs. And the basic methodology have been repeated in different countries and get roughly the same number. But that is partly based on what skills are automatable. And generally, routine skills are automatable. While social intelligence, creativity, and right now, hand-eye coordination doesn't look easy to automate. But I think the more generic way of answering it is, if your job has an easy-to-understand description, in that case, I think it's at risk of getting automated. If you can actually specify it well enough, then probably some clever engineer could construct a system to do it. If you have a job that you actually can't explain exactly what you do, then it's probably safer. So I think that's a simple heuristic for which jobs we might end up having.
So we already say that in the University of Lund, they want to pay people to do nothing for 3 days per week. And now you say we shouldn't know what people are really doing. So you should be academics, really.
I think that, you know, at some point you'll have very intelligent machines, and they'll presumably be able to replace a large proportion of the work. But that could be some time off. In the nearer term, and at the moment, I believe there isn't really much evidence that, you know, there's that much unemployment being created in this way. The unemployment rates in a lot of the Western world are pretty low at the moment by historical standards, and this fear of automation, getting rid of all the jobs and then we sort of have nothing to do, has been around a long time. I saw a documentary from the 80s from the BBC saying that, you know, in the future, in 10 years or something or other, a lot of us aren't going to have jobs due to greater automation in factories and so on. And, you know, it has been the case that it requires less people in factories to build various types of things. But it's not like the unemployment rate at the moment is all that bad, because people are doing all sorts of other things. So I think we sometimes are a little bit too worried about this idea. And another good example actually is agriculture. If you go back a few centuries, I don't remember exactly, something like 98% of people were involved in agriculture. And at the moment, it's something like 2%. You know, what happened to all those people? Well, they're, you know, the baristas and the chefs and the lecturers, and they do all sorts of interesting and useful things. And they aren't growing turnips and doing things like that anymore by hand. So yes, I think there is, you know, longer term, there is a concern here. We have to think about how we'll deal with that as a society. But in the relatively near term, I'm not too worried about it.
I think there's a couple of other things that we should worry about or think about. There's an imbalance at the moment, especially with the digital economy, between numbers of jobs and value. I don't have the figures to hand, but I think Instagram sold for £1 billion and only 9 people worked there at the time. Minecraft was employing something like 42 people, or the makers of Minecraft, and sold for £21 million, something like that, whilst a large car manufacturing company will sell for the same kinds of figures, same ballpark figures, and will employ thousands and thousands of people. So it does worry me. Longer term, I think there's a danger that we're also asking the wrong questions about this automated or artificially intelligent economy. I think we've got personal fabricators a few decades down the line, which will be sort of fabricating, printing, 3D printing what you need to buy in your own home. So all you'll be buying is the program. So the whole distribution network of kind of industrial kind of paradigm, the industrial paradigm goes. You don't need distribution at that point. You don't need mass production. You'll just need to print it off in your own home, whether that's food, medicine, whatever you like. And then the economy moves entirely into sort of intellectual property and intellectual copyright. And I think we need to be thinking about those questions and where jobs lie and where equality stands in that kind of environment, rather than in the old model of the mass production, distribution kind of economy.
Mm-hmm. Okay, thank you very much for the active participation, and thank you very much for being on the panel. We have to unfortunately conclude here, but I hope that some of the panelists will be around for the reception at 6:10. Thanks a lot.